Hey everyone, Mr. Fransky here again. Now that we've got the general idea of what a conic section is, we're going to start actually looking at how to graph some of these on a coordinate plane. So we're looking at conic parabolas here. And let's see what we got. So we know that the parabola is the conic section that we get when we intersect the plane with a cone where the plane is exactly the angle of the edge. And parabolas are kind of the simplest conic section to make equations for, so that's what we're going to start with. Remember, this goes on forever. In the downward direction, it's curved along the back of the cone because the edge of the cone is a curved shape. And there's some interesting geometry that goes along with the cone. And if you want to learn more about this, feel free to come in and talk to me because there's so much cool stuff that you can do, but it involves a lot of really kind of conceptual visualizing. So we're not going to talk a lot about it together in class, but I just want to start with this. If you had a balloon and you put the balloon inside the cone, so the parabola, imagine the parabola is like solid. Okay, so we have this solid parabola. And remember, it's not because the cone is hollow. But then you put a spherical balloon right here. Okay, so a little balloon. And you're going to start inflating that balloon. So that balloon's going to get bigger and bigger and bigger. It's a sphere. So if we end up with that sphere kind of sitting here against the parabola and also intersecting the cone, think about how it would touch the cone and how it would touch the parabola. Well, how it would touch the parabola, if you think about setting a basketball on a table, how many points does it touch the table? Exactly 1 point, right? So the sphere would touch the parabola at 1 point, and it would, the way it would touch the cone, if you think about how that balloon would expand, it would end up touching the cone at a circle right about there, right? So that would be touching the cone at a circle and touching the parabola at a point. There's special names for those things. This is the best picture of this that I could find. So here's our spherical balloon, and here's our balloon right here. This point where it touches the parabola right here is called F, because that's called the focus. Focus. Okay, so you have the focus there, and then this circle right here, called a minor circle of the sphere, that is exactly how it would intersect the cone. So notice it touches the cone here, touches the cone here. It would touch the cone all the way around. It's kind of tough visually, but trust me. If you take that circle and you take the plane, remember if you take a plane straight across, it'll create a circle. You take the plane that would create that circle, and then you take the plane of the parabola, which is this red plane right here, and where they intersect, there's a special name for that. It's called the directrix. This D right here, directrix. Direct, R-I-X. That's the directrix of the parabola. So that would be directly behind the parabola. So what you kind of have is a shape kind of like this, right? So we have our parabola. We have this directrix behind, and we have this thing called the focus on the inside. And there's some really interesting geometry with how these things relate to each other. They're going to help us graph this thing. It turns out, if I get rid of some of this extra stuff I have here, it turns out if you take any point on the parabola, and they use this point P right here, and you take the distance straight line to the directrix, like here, notice it's a right angle, okay? Straight line to the directrix, and also take the distance to the focus, right? So if you take any point, distance to the line, distance to the focus, turns out if I had drawn this better, those two distances are exactly the same. Any point on the parabola that you choose, the distance to the line, distance to the focus, those two distances are always going to be the same. And the fact that that's true is kind of cool. And that's actually how we're going to define a parabola, is that if you take any line and any point, every point that is the same distance from the line and the point, so they kind of be like in here, they create a parabola, always. They will always create a perfect parabola. If you take any point and any line, the points that are the same distance from both are always going to create a parabola. So this is our definition of parabola. A parabola is the set of all points equidistant from a line, called the directrix, and a point, called the focus. So a lot of times we're taking a parabola and finding the directrix and focus, but what this means is you can take any line, at any angle, doesn't matter, and the focus, so here's our directrix D, here's our focus F, and then every point between is going to create a parabola, every point that is the same distance. So the easiest one is the one that's kind of halfway between the two, so like right here. Okay, so that point for sure. Now, as I move to the right, I'm getting further away from the focus. So in order to keep the distance between the focus and the directrix the same, I have to move up a little bit, right? So maybe like here, that point looks like it's the same distance from the focus and directrix. Now, if I keep going right, I'm going to have to keep going up. So maybe over here, something like that. And then maybe like here, right? Because now we're kind of going up from the focus. Got to be the same distance. So maybe there. And then over here, maybe like there, there, there. And you can kind of see it's going to start creating this curved shape that ends up being a perfect parabola. And you're like, Mr. Fransky, why are we doing this? We've always learned y equals x squared is a parabola. You graph it like this. You can move it left, right. You can do vertical stretches, shrinks, whatever, vertex form. We've done this before. This is a unique way of thinking about a parabola in terms of how it's related to this cone. And the way that you can prove that that sphere and the plane where it intersects behind is a really cool proof, but it's beyond the scope of this class. So if you want to talk about it, please come in, because there's some cool animations I can show you that kind of show this. But for now, just trust me, we have this idea that the distance from the directrix at a straight line, so right angle there, and to the focus, those two have the exact same length, okay? Clearly this is not a perfect drawing, but that's just the idea. So now, how are we actually going to get an equation for this thing? So if I wanted to actually think about this on like a coordinate plane, okay, so we had a coordinate plane, let's say the vertex is that special point between that is halfway between the focus and the directrix, is on 0, 0, and we know that the C value is up here, and we have a directrix down here, so our parabola is kind of in here like this. So we're going to say, what's the equation for this parabola? How can we figure it out based on this distance C? So what I'm going to do is I'm going to kind of plot that same picture, but I'm not going to use some coordinate pairs. Let's say the focus is at 0, C, right? So C would be a y coordinate up here. Here's our vertex at 0, 0. Our parabola is in here like this, something like that. Okay, and then our directrix is down here at y equals negative C, right? Because we have a distance of C here. Didn't draw that in the perfect spot. Let's do a little bit better. Should be a little closer, so more like here maybe, huh? So this is y equals negative C. So this distance is C down here as well. So what we're saying is we take any point right here, we'll call it P, or point x, y, x comma y, that the distance here and the distance here should be the same. Okay, let's call this D1, call this D2. Well, D1 is going to have to use distance formula. We'll get that in a second. But D2, I think, is going to be easier to find because it's a straight line, right? It's like a perfect vertical line. So D2 is just going to be, this distance right here is C, right? So we have C plus the distance from here to the curve. That's just the vertical coordinate of this point, which is y. So D2 is C plus y. Right, C from here to here. Let's kind of get some colors in here. So this distance right here is the C. And then this distance right here is the y. Right, so C plus y gives me that vertical distance. Now this guy over here we're going to have to use distance formula for. So D1 is going to be equal to the square root of x minus 0 squared plus y minus c squared. Now, I can hear all of your voices. You're saying, do we have to know this? No. This is a proof at proof. So if you want to skip the rest of this proof till we get to the formula, you can do that. But we have these two distances. We're just going to set them equal to each other and do some algebra now. So if I make D1 equal to D2, we'll have C plus y is equal to the square root, I guess I'm flipping it around, D2 equal to D1, square root of x squared plus y minus c squared. Now I'm going to do something to square both sides. So square this side, square this side. So I'm going to expand it out as well. So I have c squared plus 2cy plus y squared, right? Because you guys would never say this is c squared plus y squared because puppies would die, right? So we have to expand this out. You could FOIL it if you need to, but it's really nice to have this in your random access memory. First thing squared plus 2 times the first times the second plus the second thing squared. Right side, the square root disappears, and I'm going to expand out this y minus c squared. So that's going to be y squared minus 2cy plus c squared. Beautiful thing about this is a lot of stuff just disappears. The c squared we can subtract from both sides. The y squared we can subtract from both sides. Now what I'm going to do is add 2cy to both sides, so it disappears from this side. So plus 2cy plus 2cy. And I end up with x squared is equal to 4cy. And this is the general form, or the standard form for a parabola. Standard form for a parabola. And again, you might be saying, Mr. Fransky, this looks different than things we've had before with parabolas. We haven't had this C involved. What this is telling us is if we know where the focus is, or if we know where the directrix is, we can find an equation for the parabola. It's kind of cool. So let's get this kind of in general, a general idea of what's going on here. So any vertical parabola is x squared equals 4cy. If the c is positive, for example, if we have x squared equals 8y, right? So 8 is our 4c. In this case, the c would be 2. Right? Because 4c is 8. You can always solve that over here on the side if you want to. 4c is 8, so then divide by 4. C must be 2. So, if that was the case, we'd have c up here at 2. We'd have our directrix at negative 2. Okay, we have a positive c value. It's going to open upwards. It's going to have a parabola looking like this. Okay, it doesn't have to be perfect. What I always say is that it hugs the focus. Okay, so it hugs the focus. So always make sure that your parabola is going towards the focus, right? It's focusing on the focus. Okay, never going to go like across the directrix. So it's going to focus on the focus. The vertex is exactly halfway in between. Okay, vertex is exactly halfway between the focus and directrix. For this case, it's going to be at 0, 0. Tomorrow, we're going to talk about if we move this, you would have like an x minus h situation and a y minus k, right? We'll talk about that tomorrow. But for now, we're going to have everything centered at 0, 0. If c is negative, it's going to open down. All that means is that your c value is down here, right? So this is going to be 0c. Here, this would be 0c. Right, so this would be like, I don't know, x squared equals negative 16y, something like that, right? So then our directrix would be up above, right? Because the directrix always backs up the parabola. So parabola looks something like that. Hugs the focus. Negative c value opens downward. One other thing I want to talk about with parabolas is called the focal length. It's the distance across the parabola at the focus. Let's use some technology here. Okay, so that length right there. Let's think about what that length is going to be. Right? And I have the answer here, but let's think about why it's that. Remember, this distance here has got to be the same as this distance here, right? Well, this distance here it's c, and if we're at the focus, if we're crossing the focus, this distance is c as well. So what's that total distance? Well, it's 2c. So that must mean that this distance is 2c, and it's because of symmetry, this is also 2c, so the whole distance across 4c. Same thing here, focal length. The way that they do that is sometimes they'll tell you the focal length. They're like, the focal length is 20. So then you can solve for c. If the focal length is 20, then the c value is 5. Or it could be negative 5, right? They would have to tell you if it opens up or opens down, something like that. All right, you can also have sideways parabolas, right? We are not going to focus too much on the ones that are like angled, because they're just harder to deal with. You can deal with rotating functions. You can look up on YouTube if you want to. But if we have a y squared equals 4cx, it's just going to open to the left or open to the right. So what that's going to look like, if we have a c that's positive, makes sense to me it would be on the positive x-axis. So we'd have a focus at c0, and we'd have a directrix over here behind the parabola. It's going to open to the right like that. Some of you, if you read your book, you'll notice they use P instead of C, but when they talk about hyperbolas and ellipses, they use C. I don't know why they switch it up, but I prefer just to keep everything as a C. So if you want to change it up, that's just fine. It's up to you. They also have lots of formulas to memorize. You'll notice I do everything visually. So they have like 8 formulas to memorize for these parabolas. I'm just like, dude, it's either y squared equals 4cx or x squared equals 4cy. If the c is positive, it's either right or up. If it's negative, it's left or down. And you can kind of draw a picture to kind of figure it out. Drawing a picture, super, super important in this unit because it just gives you a picture of what's going on. If c is negative now, we're going to open to the left. So over here, we're at negative c0. And over here, we have our directrix be opening like that. Okay. Vertex at 0, 0. Focal length, once again, distance across the focus. Use our blue again for that. There it is, 4c, 4c. Okay. That distance is 4c, that distance is 4c. All right, let's try some problems, finally. So find the focus, directrix, and focal width for the parabola, y equals negative 1/12 x squared. This is a bit more like we're used to, right? We have this negative 1/12, that means it's flipped over the x-axis, and it has a vertical shrink, but I'm going to write it in what we called standard form. So I'm going to write negative 12y equals x squared, or x squared equals negative 12y. Because now this is in my x squared equals 4cy. So which way does this thing open? Well, it's an x squared, so it's going to be an up-down. Going to be an up-down parabola, right? I don't think I really mentioned that, but we have vertical or up-down parabolas, right? Because we're up or down. And then we have the sideways, or I call them side-to-side sometimes, side-to-side. Because either opening left or opening right. Okay. So in this case, we have x squared equals 4cy, so it's going to be an up or a down. We have a negative c value, so it's going to be opening down. Okay. So let's see. 4c is negative 12. So what's c? c is negative 3. So going to be down 1, 2, 3. There's our focus, and then up 1, 2, 3 is going to be our directrix. And there is our parabola. Okay. So focus. Focus is at 0, negative 3. Careful about mixing up your x's and y's. The directrix is at y equals 3. The focal width is distance across, is equal to absolute value of 4c, which is equal to 12. Notice you can just steal it from right here, right? And just do the absolute value, right? So you have your 4cy. 4c is right here, so that's the focal length. Focal width, excuse me. And we sketch a graph. That's it. We're done. Let's take a look at one more. Find the equation for the parabola with directrix x equals 2 and focus -2, 0. I love these problems. It's like a puzzle. You draw on what you know. X equals 2. That's a vertical line at 2. Don't mix up your vertical and horizontal lines. X equals vertical line. Vertical is spelled C-A-L, not C-L-E. Focus is at -2, 0 right there. So how is this thing opening? This thing is opening left. Notice I learned that just by graphing, right? I drew a picture of what I knew. Okay, so we're opening to the left. C is -2, right? C is -2 because we're opening left. Our focus is negative. It's on the left side. Directrix is x equals 2. We have that right here. They told us that. So we have our C. We know it's going to be a y squared equals 4cx. So in this case, it's going to be y squared equals 4 times -2x, which is y squared equals -8x. And we are done. Only other type of problem you might see in your homework, they might give you the focal width. So they tell you the focal width, just remember that's always equal to absolute value of 4c. So it could be a positive or negative c. Draw a picture, see what kind of information they give you. I love conics. We have so much fun ahead of us. I love you guys so much. That's why I'm here. Have an excellent day.